Welcome to Lesson 13C, Introduction to Particles, Part 1. For Part 1 of this lesson, we are going to watch about a 22-minute PowerPoint presentation about particles called Introduction to Particles. There is a PDF file with thumbnail slides of this PowerPoint presentation on the website that you can download. We'll talk about particle size and the range in microns or micrometers, how particles interact with light, how particles interact with our lungs when we breathe in particles, and what various particles look like, just a lot of pictures. And in the next lesson, Part 2, we'll summarize some of the main points from this presentation. So without further ado, I will start the PowerPoint presentation. Here's a quick presentation about particles. Particle sizes are expressed in units of microns or micrometers, which is a millionth of a meter. And we'll talk about all these things, diameters and some definitions and terminology, how they interact with the human body and with light. And I'll show a bunch of images also. So let's start with this slide, which is particle diameters in microns. Notice this is a log scale. So here's particle diameter, dp, we call that, or just diameter. And we have 1 micron in the middle. And this is a log scale, so 10, 100, 1,000 microns is a millimeter, 10,000 microns is a centimeter. If you go the other way, 0.1, 0.01, 0.001 is a nanometer. And let's look at some particles that are well known, like water. Water particles can range from about 2 to 10,000 microns. So the tiniest ones are little water droplets in clouds and fog. Then we have mist, drizzle. When you get into rain, these are hundreds of microns, all the way up to about a centimeter can be rain. We can also use human hair as a benchmark. 30 to 200 microns is typical of human hair, depending on the color of your hair, actually, the type of hair. Blonde, thin hair is very tiny diameter, like that would be the 30, very blonde hair. Dark hair is typically much thicker, 200 microns. EPA puts out this little diagram to give you an illustration of a human hair. This one is at about 60 microns, like I said, about in the middle of that range. And then PM10 is called particulate matter. That's less than 10 microns. That would be these blue particles compared to a human hair. The little reddish purplish ones here are 2.5 microns. We call them PM2.5. This is just a magnified view of that. So 4 of them fit within 10 micron across. And just for comparison, here's the really fine beach sand that you can barely see. I'm kind of a hairy guy, so I have lots of hair on my arms. If I go to the beach, I get these little tiny grains of sand caught in my hair. So those are around 90 microns, the smallest ones. Let me do a couple dividing lines here. 10 microns is a common dividing line, right here, this red line. And then some of the particles that are kind of centered around 10 microns are fly ash, coal dust, cement dust, milled flour. If you take milled flour, they can range all the way from a micron to about 100 microns and anywhere in between. So there's a lot of range of sizes. Talcum powder's about there too, but these are centered around 10 microns. So that's a common dividing line. Why is that? Well, it turns out that anything bigger than 10 microns we call non-inhalable because you can't get them into your breathing system. These particles, they're fairly big. They would get caught in your nose hairs or in the back of your throat if you're breathing with your mouth. They don't get into your lungs, whereas inhalable particles are less than 10 microns. The EPA is concerned about those. They call them PM10, particulate matter less than 10 microns. That's what PM10 means. So particles less than 10 microns are inhalable. Particles greater than 10 microns do not get inhaled into the lungs. And then they also call them coarse particles. They are of concern, and they are labeled particulate matter less than 10 microns, PM10. These PM10 particles are among the 7 criteria air pollutants, or CAPs, and those are defined as air pollutants for which the EPA has NAAQS, which are National Ambient Air Quality Standards. So PM10 is one of the 7 CAPs. 2.5 microns is another common dividing line. So that's this red line right here at 2.5 microns. Some of the particles that are centered around that, bacteria has a range like that, insecticide dust, sulfuric concentrator mist. And so why are we concerned about that? Well, anything less than 2.5 microns is called PM2.5, and those are called fine particles or fines. Anything bigger than 2.5 but less than 10 is right in this range, is called inhalable. They're not respirable yet, but they're inhalable coarse particles. They're still called coarse particles. They're less than 10 microns. You have to be less than 10 and 2.5 microns to be fine particles. Particles less than 2.5 microns are called respirable. That's a little different than inhalable. They can penetrate deep into the lungs. and so they're potentially more problematic for human health than the PM10 were. EPA calls these fine particles or fines, or PM2.5. They're also one of the 7 caps. And finally, let's use 1 micron as a dividing line right in the middle of this chart. Submicron particles, they mean they're less than 1 micron, as the name implies. The ones I identified here are due to combustion. Resins, rosin smoke, oil smokes, tobacco smokes, zinc oxide fumes. These are all due to combustion, and they're smaller than a micron, whereas supermicron particles bigger than a micron are things that are mechanically ground down, such as coal dust, cement dust, pulverized coal, talcum powder, gets a little bit below 1 micron, milled flour. So why do these all have their left border right around a micron? Well, it turns out, and I'll use coffee as an example. Suppose you have coffee beans, and I like to drink coffee. I like very dark and strong coffee. So I get some of my dark coffee beans and I start grinding. Okay, I have a grinder. So I grind and grind and grind. What happens is the little particles can't get down to about a micron and they can't break anymore. There's just a kind of a fundamental limit to how small particles can break. Once they get to 1 micron, they're not going to break anymore. I can grind in my coffee grinder for 3 hours and I'm still not going to get any finer than about a micron. It's kind of a physical limit. In kind of summary, combustion or burning produces mostly submicron particles. Natural process such as grinding, crushing, produce supermicron particles. Particles less than a micron can penetrate really deep into the lungs. Now, they're not considered one of the caps. The caps stop at 2.5, so 1 micron particles are within the PM2.5. So they're part of that. There's not a special classification by themselves, but these can get all the way into the alveoli and they're potentially very problematic for human health. They also interact most with visible light and light waves. This is the visible spectrum of light from about 0.4 microns roughly to 0.7 microns. Actually 0.33 is more accurate to 0.7 is the wavelength of light from the ultraviolet up to the infrared and beyond that. This is infrared beyond here, ultraviolet that way. And so all the colors of the rainbows that you see are due to refraction of light rays through raindrops right after it rains. We all enjoy a rainbow. So you can see that the reds and violets and then the yellows, greens, and blues. So how small of a particle can you see with your naked eye? Well, if you take a whole bunch of people and you get a piece of white paper and you put a red dot or a black dot and they keep changing the size, various sizes of dots, what's the smallest dot? You can see this period here, but what if we had a really, really tiny little dot on a piece of paper? You take a whole bunch of healthy people with healthy eyes, not old people, but like me, but younger people with healthy eyes, and you measure, the range is pretty big from 20 to 100 microns. So let's call it 70 microns as the average, which is about the size of a single strand of hair. If you cut that hair into like a little tiny dot, you'd be able to see that. However, if the particle is glowing, so it's scattering light, say you have bubbles or some kind of particles that are transparent or translucent, they scatter and reflect sunlight. A healthy human eye can see down to about 10 microns. So when they're glowing and scattering light, they kind of look bigger and you can see them. So we're going to use that 10 micron as a benchmark. The naked eye can see individual air pollution particles down to about 10 microns. So most air pollution particles from burning, as we just learned, is about 1 micron or smaller. So how do we see that? We don't see the individual particles when they're that small, 1 micron, or when they're actually anything less than about 10 microns. We can't see those particles, but we can see clouds of them. So even submicron particles, we can see if there's billions of them in the air. I like to use this as a comparison of wavelengths of light. So here's lambda, which is the wavelength of light. And these particle sizes, little, big, and medium. In the first case, think of a particle being very small compared to lambda. And so that's like the analogy here is a boat, a little tiny boat bobbing on huge waves. So it just kind of bobs up and down. If you've ever been on the ocean and you're just kind of laying there when it's nice and calm, but there's these kind of waves that just bob you up and down. There's not much interaction there. When you have a huge particle compared to lambda, in other words, take a big cruise ship and the waves are just kind of lapping against the side of the ship. Again, there's not much interaction. The ship will block that part of the water, the waves, but the waves are not affecting the ship. This would be a huge particle that blocks the light, but it doesn't interact that much. However, when the particles are about the same size as the wavelength, there's a lot of interaction. And so if you have a boat or a ship that's about the same size as the waves, then you get a lot of interaction between them. There's the Wreck of the Edmund Fitzgerald by Gordon Lightfoot. What happens is on Lake Superior, this is a true story, this boat and ships on Lake Superior, when there's big storms, these waves are about the same size as the ship. And so the ship gets tossed back and forth by these waves, and a lot of times they capsize. Well, the same thing happens with light. And even if you plot light attenuation versus particle size, you see that the peak attenuation is right around this 0.4 or so microns. And here's the visible light band. And so they're not exactly on top of each other, but the point is, visible light is also light that is attenuated by particles most significantly. So that's why we see particles that are combusted in smoke. These particles are usually around this range, under a micron, around here. So we see those. Let me just briefly look at the human respiratory system. You breathe with your mouth or your nose, and then your air goes down through the trachea into these bronchial tubes, and then it keeps branching and branching and branching about 20 times or more until you get to these little alveoli sacs at the bottom of your lungs. So these sacs are like little balloons that where the gases exchange between the air and your blood. There's little capillaries in there that exchange the gas. If you look at a 3D kind of view, it does look like a tree. We call it the bronchial tree because of its shape. And so there's two regions. The tracheobronchial region is this pipe network, the bronchial tubes. And so again, as I said, they keep branching about 20 times, divided in two. We're showing 1/2, and then we don't show all the alveoli, but these keep branching and getting all three-dimensional like that tree until you get to the alveoli sacs. Now, when you inhale air, there's always particles in the air. Right now I'm sitting here, there's particles in this room floating around. Some of them I breathe, they go into my bronchial tubes, they come down here. And what happens is sometimes those particles will keep going, but they'll eventually come to a turn, say this turn right here, and the particle, because of inertia, cannot make that turn. So it slams against the wall of the bronchial tube. Well, the bronchial tubes are lined with mucus, and so the particle will stick there when it hits. And the bronchial tubes, the inside of the tube, also has these little hairs called cilia, and they kind of slowly beat and they push the particles up and out of the lungs. So they'll push the particles right up the bronchial tubes into the trachea, into the back of your throat. So every time you swallow, you're swallowing particles that had been in your lungs, but slowly work their way back up. And this is good because if you didn't have that, your bronchial tubes would keep filling with particles and you'd eventually suffocate without having that mechanism. Here's just some pictures of bronchial tubes and some of the cilia. Here's a close-up electron microscope kind of image of cilia, these little hairs. So you see they're like fur almost. They're all over the inside lining of your bronchial tubes. And here's some particles, and these cilia are kind of moving and pushing those particles up. They know which way is up, and they take those particles right up to your throat. Once we get all the way down to the alveoli, these are little grape-like structures here. They're kind of like balloons, and they expand and contract. So when you breathe and your lungs expand, your chest gets bigger. That's these alveoli filling up with air. Now, this is where there's a lot of capillaries and the gases are exchanged with the blood. The total area of these alveoli is about 100 square meters. I looked up the surface of a tennis court is about 261 square meters. So roughly half of the surface of a tennis court. Alveoli are too small to have cilia. If you get particles that actually, the little tiny particles like submicron particles can get all the way into these little sacs through all the bronchial tubes. They make all these turns and then they finally get down into the alveoli. You can't get them out with cilia. There's no cilia in the alveoli, but there are white blood cells called macrophage which can attack the particles and kind of digest them. So that's the purpose of those macrophage. Here's some pictures. A cross-section of the lung looks kind of like a sponge, I think. There's a bronchial tube and then the alveoli and membranes between them. Here's a close-up of that. Membranes, there's lots of pores, so we draw them like balloons, but they're really interconnected with all these pores to keep the pressure constant throughout your lungs when you breathe in and out. And so these are the alveoli sacs in cross-section, and then the membranes. The capillaries are in these membranes where the gas can actually go across the membrane into your bloodstream. Oxygen goes into your blood from the alveoli through the membrane into your capillary tubes, and then it goes to your cells throughout your body, and then carbon dioxide goes back into your alveoli, and then you exhale that. Another electron microscope image of that same thing. So this is kind kind of a summary of the sizes. Particles greater than about 10 microns are not inhalable. Inhalable coarse particles between 2.5 and 10 microns get into the tracheobronchial region, and those are expelled by the cilia. When you get down to supermicron fine particles, so between 1 and 2.5 microns, they can penetrate down to the smallest bronchial tubes, and they have a more difficult time, but they can usually be expelled by the cilia. And then finally, the submicron particles are less than a micron, and those can enter the alveoli, and the macrophage is the way the body can remove those particles. So even a healthy human lung can have particles that build up. Sometimes there's certain particles that come into your lungs, and the cilia can't remove them in the bronchial tubes, or they get down into the alveoli and the macrophage can't digest them. So they stay in your body the rest of your life. So if you take an autopsy of someone that was healthy, had healthy lungs, at least this person was healthy before he died, and they did the autopsy, there are some black areas here that are particles that just got in his or her lungs. I don't know what kind of person this was. Compare that to someone with a lot of particles, probably a heavy smoker. Some of the tars and stuff from cigarettes are like this. They don't get removed. They can't get removed by the cilia or by the macrophage, so they stay in your lungs. And so this looks like about half of this person's lungs are blackened by these particles, and therefore there's no gas exchange taking place with the alveoli. So you take that 100 square meters, half a tennis court, now you have about a fourth of a tennis court. So that's why people with this kind of lung will have COPD and other respiratory problems. Now there's a book called The Particle Atlas, and this is all online now. But back in the day, I scanned all these pictures in and just want to show you some pictures of various particles. In all these cases, you have different magnifications. So here it's a 125x. So based on that and the size of the picture, I calculated what the size of 10 micron particle would look like. So you always see this red dot. It'll change in size as the magnification changes. So this is 10 microns. That'll be our reference, that 10 microns. We have hairs between about 50 and 150 microns. Here's human hair after shaving with an electric razor. So there's the hair particles. There's our 10 micron reference. And what are all these things? Well, there's skin flakes and pieces of dirt and stuff that came as you shave. And some of these can be a lot smaller than the hairs themselves, as you can see. Asbestos, the actual shaft here is pretty big. As you can see, that's much bigger than 10 microns. But these little hairy fibrils that come off of asbestos, these are little rods, and they can be small, very small, down to a micron or so. They're also very brittle, so they break easily, and they're cylindrical shaped instead of spherical. So you imagine taking one of these little rods and breaking it into little pieces. They get in your lungs. They're very kind of stiff, like little pieces of glass. They can penetrate through the membranes and get stuck in your bronchial tubes, and some of the tiniest ones can get down deep into your bronchial tubes. And then even if they get down into the alveoli, the macrophage can't take them out. Cilia have a hard time getting these out because of their shape, their rods. And the worst part of it is that they're cancerous. So you don't want to be breathing asbestos dust. So nowadays, whenever they take asbestos out of buildings, it used to be used for insulation, by the way, in pipe insulation in buildings. So sometimes when they're going to demolish a building, they'll take all the asbestos out first, send in people with hazmat suits to take out the asbestos. Compare that with fiberglass. They're about 10 microns in diameter, and they're long and straight, but they have no fibrils. They're nice and smooth. And even when they're all broken apart, this is what you breathe in your attic if you have fiberglass insulation, this dust. This is called a fiberglass dust. And these are all bigger than 10 microns. So they're 10 to 25 microns generally. And they can get in your back of your throat and stuff, but they're not going to really get in your lungs. They can irritate, make you cough. But I would much rather breathe this than asbestos. You basically cough it out when it gets down in there. Here's some pollen, ragweed pollen, 500x. So here's my 10 micron scale. So they're about 20 microns in size. And so those you really don't get into your lungs. They can get stuck in your nose and give you some allergies and stuff like that, but they're not going to get into your lungs. Dandelion pollen is even bigger, 25 microns. Molds are interesting. There's a shaft. This shaft is about 10 microns, you can see there. This head is about 40 microns. But these little spores that come off, you can see all these spores on the head and they fall off. There, in this particular mold are about 4 microns. And so those can get into your lungs. And usually molds cause allergies and other respiratory problems, but some of them can actually be deadly. And I like to give the example of hurricanes in the south, like Louisiana, New Orleans area is often hit with hurricanes every season, and then houses are flooded. They go in and all the drywall plaster is covered in mold. And as they start tearing that out to repair it, people have died from some of this mold. Some of this mold can be deadly. So it gets into your lungs, they breathe it, and it can cause all kind of problems, even death. So you got to be careful about molds. Of course, coronavirus in 2020 was always in the news. It's about 125 nanometers or 0.125 microns, and has these little crowns or spikes, which is why they call it coronavirus. And my 10 micron particle, I couldn't even draw it. This is, you can see the arc of it. It's a huge particle. 10 microns is huge compared to 0.125 microns. These are very, very small particles. They're actually big for as far as viruses go, but they're very small compared to our 10 microns. Here's my ground coffee that I was talking about. This is some piece of dirt or something, but the ground coffee itself has some very small particles, but they're typically much bigger than a micron. And if you keep grinding them, you can get some of these to break further, but they're never going to get smaller than a micron. Deodorant spray, powder, or talcum powder, similar, various sizes, all greater than a micron. If you burn coal, and it's not a very efficient process under fed coal stoker, you'll have all these unburned pieces of coal. You'll have little pieces of rocks or minerals that haven't burned. And then you'll see some of these round particles. Coal has vaporized, and then it recondenses. And when it recondenses, it forms a drop, a round drop, and then it might solidify. So you can get these little tiny particles that are round. You see that these were once vapors. And so those can be all the way down. Some of these particles can be from down to a micron or so if it's underfed. Ammonium sulfate is interesting because these are not round. They're kind of cereal flake shaped, and they're 10 to 100 microns. These are big guys, and they're not round. We have ways of dealing with non-round shaped particles. And that's the end, so I will stop there. Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3. That's all there is to it.